Hi everybody, and welcome to example 7. We are still looking at page 52 in the workbook here. This is going to be an example where we try to verify theorem 2.14 in a specific example. Okay, so let's read example 7 together here. So as in part A of example 5, we're going to define a linear transformation like this, okay, where beta and gamma are given to us to be these two bases. Okay, so we're referring back to example 5. Few pages ago. Use the matrix that we calculated in part A of example 5 to verify theorem 2.14 for this particular vector. Okay, so as we do this, keep in mind that it's this equation that we want to verify. There are three things that we really need to calculate. Okay, so this coordinate vector, this matrix, and this coordinate vector. All right, we'll kind of attack those one at a time here. So how about if we start with the coordinate vector of u relative to beta? Okay, well, here's our basis beta. And so to find that coordinate vector, we need to write u as a linear combination of those things. So let's start there. So u equals 1, 2, 3. And we want to write that as a linear combination of 1, 1, 1, 1, 1, 0, and finally 1, 0, 0. Okay, we've done this type of problem before. Okay, so we could maybe start with, let's see, which coordinate would be the easiest to start with here? Probably the third coordinate. We want to get a 3 there. Notice that there are zeros here and here, so that kind of forces us to put a 3 here, so that 3 times this 1 gives us the 3 that we need. Okay. What's next here? So then we'd like to get a 2 there. So we've already got a 3 times a 1 in the second coordinate. So 3 times 1, we would need to subtract 1 from that, okay, to get a 2. All right, and then finally to get this 1 here, let's see. Now we're looking at the first coordinate. So we've got a 3 times a 1 plus a negative 1 times a 1. That's 3 minus 1 is 2, and we want to get a 1, so it looks like we need a negative 1 over here to make that happen. All right, so we've got our blanks filled in, and so far what we know then is that the coordinates of u relative to our basis beta look like 3, negative 1, negative 1, transpose. Okay. So far, what we've got then is this. Okay, we know what u beta is. All right, next thing, let's see, what could we look at next here? Maybe the coordinate vector over here, t of u relative to gamma. Okay, so we need to do two things to calculate that. We need to first calculate t of u, and then figure out what its coordinates are. All right, so t of u looks like t of 1, 2, 3. Okay, and our formula for t is sitting here, so we just need to substitute in 1, 2, and 3 for a1, a2, and a3. Okay, and I'll let you confirm that when you do that, you're going to get 5 in the first coordinate and 7 in the second. Okay, we want to write that as a linear combination of the other basis gamma. Okay, and notice that since that's the standard basis, that's not hard to do. We're just going to get 5 times 1, 0, plus 7 times 0, 1. Okay, so there are our coordinates. And so the coordinates of t of u relative to gamma would look like 5, 7. Okay, so far, here's where we're at. We know we have just calculated these two things. And what's nice is that this matrix, we already calculated that back in example 5. We don't need to repeat that calculation, so we are ready to verify here. Okay, therefore, and yeah, sorry for all of this scrolling, but I just want to make sure that you see what we're doing here. Okay, we're going to start with the right-hand side of the equation, this. Calculate that and just confirm that that's equal to what's over here. All right, so let's do that. So t, the matrix t going from beta to gamma times the coordinate vector of u is, okay, 3, 3, 1, 2, negative 1, 0. I am looking back at the calculation that we did in example 5. Okay, so that matrix didn't come out of the air. We calculated that earlier in a previous example. Okay, we're going to take that, and multiply it by u beta, which we calculated up here. 3, negative 1, negative 1. Okay, that's a matrix multiplication problem. If you just take the matrix on the left and multiply by the vector, you can confirm that you're going to get 5, 7. Okay, and then notice that 5, 7, sure enough, that's equal to the coordinate vector of t of u relative to gamma. Okay, and we have just shown that this is equal to that. That verifies theorem 2.14. Okay. I'm going to try to be a little bit neater here. Okay, so that verifies theorem 2.14, and we're done.